Hello everyone. So in this video we are going to talk about a very important topic in classical mechanics known as phase space trajectory. Phase space trajectory या PST जिसको हम बोलते हैं is a very interesting kind of a topic because this gives us a very different and a very interesting perspective as to the motion of certain kind of standard objects. इस वीडियो में हम चार स्टैंडर्ड प्रॉब्लम्स को स्टडी करने जा रहे हैं. वन इज अ स्प्रिंग मास सिस्टम, अनदर इज अ सिंपल पेंडुलम, another is the inverted well potential and one is a double well potential. Now ये जो systems है इसको शायद आपने कभी usually देखा होगा and you probably would have studied these systems, especially spring mass system हो गया या फिर simple pendulum हो गया. You're familiar with these systems. But what about the phase space trajectory of these particular systems? Now phase space trajectory सबसे पहले होता क्या है? You see, whenever we study different kinds of physical systems, we are usually interested in the position or the displacement of a system. So for example, अगर हम कोई 1D motion को ले लेते हैं, then we are usually interested in, let's suppose, the variation of the position of the particle with respect to time. That is what we are usually interested in. Sometimes we are also interested in velocity, where variation with respect to time. Now that is only part of the information. You see, there is other hidden information in the system that we are interested in, that we want to study. So when we talk about position and the variation of a position of a system with respect to time, that limits our attention to configuration space. Now there is another space that is associated with the particle's motion, which is the momentum space. Momentum space माने when we look at the velocity of the particle or the momentum of the particle and how it changes with time. What is interesting is that the position space or the configuration space and the momentum space, they are connected to each other. You know, there is an interesting relationship that is between the position and the momentum of a particle as a system evolves. तो वही हम आज देखने जा रहे हैं. That is what we are going to study today. कि सबसे पहले phase space या phase space diagram या phase space trajectory होता क्या है, and then I will show you how to derive the phase space equations and how to plot the phase space trajectories of four standard systems: spring mass system, simple pendulum, inverted potential well and a double well potential. ठीक है. So सबसे पहले what is a phase space trajectory? जैसा मैंने आपको बोला, usually we are interested in the position and the variation of a position of a particle with respect to time. And when we do that, when we find out the position with respect to time, we call that as the trajectory of the particle. है ना? कहाँ पे particle होगा, किस तरह का पाथ वो ट्रेस करेगा, that is what we call the trajectory of a particle. However, if we can find out also the momentum and how the momentum of a particle changes with respect to time, and then we can combine the relationship between these two. ठीक है, हम टाइम को रिमूव कर देते हैं. We remove time as an explicit parameter to, let's suppose, an implicit parameter, and then we try to find out a relationship between x versus p या फिर px. Then that kind of an equation that gives us a relationship between x and px is known as the equation of PST or equation of phase space trajectory. And the diagram, if we plot that kind of an equation in a graph where x-axis में x होगा, y-axis में px होगा, then that would be a phase space diagram or a phase space trajectory. Okay, or we call it phase space diagram. ठीक है. Now ये जरूरी नहीं है कि हम x और px के बीच में ही relationships को find out करने की कोशिश कर रहे हैं, because different systems can have different kind of variables. Spring mass system can have displacement along x-axis. Pendulum can have displacement along theta axis. Some other system can have displacements along other kinds of quantities. So as long as we are interested in the change of the coordinate versus momenta and we are interested in their relationships, then that would correspond to understanding of the motion in phase space. So for example, we can be interested in y versus py, z versus pz, or r versus, you know, momenta along the radial direction, theta versus p theta. Yeah, in general I can say q, which is a coordinate, versus p. All right. So a phase space diagram is essentially something that gives us information about the variation of the, position and the momentum of a particular system as it evolves with respect to time. So मैं कुछ notes दे दूँ आपको? Should I go on giving you notes? All right, so we'll make it a little bit of a detailed video. I'll give you notes as we go along. So a small note here. If we eliminate time, let's suppose we are interested in we have found out the position, okay, of a particle as it changes with time. We have found out the momentum of a particle or the velocity of a particle as it changes with time. But now we remove the time as an explicit time of its explicit dependence and get x versus px or vice versa, then such a trajectory is called phase space trajectory or phase space diagram, and the equations corresponding to it are called equations of PST. Okay, equations of PST. All right, let's go ahead into some standard systems. मैं systems को जब detail में explain करूँगा एक एक करके, we look at its motion and we look at the corresponding phase space diagram. Then अपने आप आपको एक clarity develop हो जाएगी regarding what's going on. अगर अब तक आपको थोड़ा सा भी confusion है, तो you will feel much more clearer as we discuss these cases. So case studies. Okay, we are going to do 4 case studies today. तो पहला जो case study है, that is the spring mass system. ठीक है, spring mass system is a very common problem. We are mostly familiar with what a spring mass system is. It is a very good example of a harmonic oscillator, because we get oscillations about an equilibrium. So मेरे पास अगर एक spring mass system है, and I'll keep it very simple, okay? I'll say that the spring is along the horizontal direction like this. There is a point mass associated with it like this. Okay, so we have a point mass m and a spring having spring constant k. तो point mass का जो variation होगा, the variation will be along the x-axis. All right, very simple. We are familiar with its motion because it's a harmonic oscillator. अगर मैं इसको थोड़ा सा भी displace कर देता हूँ, तो it starts oscillating about its equilibrium point. As long as there is no dissipation involved, it will keep on oscillating in a sinusoidal manner. So this is a perfect example of simple harmonic oscillations. However, we are interested in the phase space diagram. तो उसके लिए हम क्या करेंगे? First of all, we will look at its Hamiltonian or total energy. So if I want to calculate its total energy, what is the total energy? Kinetic energy plus the potential energy is equal to the total energy. All right. So what is kinetic energy? Kinetic energy is simply equal to p square upon 2m. All right, half mv square can be written as p square upon 2m, where p is the momentum. And potential energy is simply half kx square, okay, is equal to E. This is essentially the energy equation, जहाँ पे energy क्या है? अगर कोई भी dissipation नहीं है, कोई भी drag forces नहीं है, it is an ideal system and it is not losing energy as movement takes place, so we can call it as a system that does not lose energy. So the energy remains constant energy system. All right. So there we have it. We already have this equation. दिख रहा है आपको? You see the momentum here. You see x here. Everything else is a constant. E is a constant. K is a constant. M is a constant. So this is the equation of PST. इसको थोड़ा मैं rearrange करके दिखाता हूँ आपको. Let me just rearrange it a little bit. So p square upon 2m plus x square upon 2e upon k हो जाएगा is equal to 1. थोड़ा सा मैं और रीअरेंज कर देता हूं. लेट्स सपोज x को मैं पहले लेके आता हूं बिकॉज दैट विल कॉरेस्पॉन्ड टू द x एक्सिस. सो x अपॉन लेट्स सपोज रूट ओवर 2e अपॉन k होल स्क्वायर प्लस p अपॉन यहां पे e आएगा, राइट, यहां पे e आएगा 2me रूट ओवर whole square is equal to 1. This is the equation of phase space diagram corresponding to a spring mass system. Now you may say this looks very complicated, है ना, इतने सारे terms हैं, it seems very complicated, but it actually is not. I mean, थोड़ा सा ध्यान से देखिए. Are you able to recognize it looks like what kind of an equation? It looks like what kind of an equation? तो मैं आपको एक एग्जाम्पल देता हूं. अगर मैं आपको एक एग्जाम्पल देता हूं, लेट्स सपोज x अपॉन a होल स्क्वायर प्लस y अपॉन b होल स्क्वायर इज इक्वल टू 1, then this is the equation of what? This is the equation of an ellipse. It's a very standard equation of an ellipse which is centered around 0 0 having semi major axis a and semi minor axis b. तो यहां पे a क्या है? a is the semi major axis. ओके, सेमी मेजर एक्सिस मतलब जो एलिप्स का लॉन्गिट्यूडिनल लेंथ होता है, जो लंबा लेंथ होता है उसका हाफ, और सेमी माइनर एक्सिस का मतलब है जो शॉर्टर लेंथ होता है उसका हाफ, सेमी माइनर एक्सिस. सो देयरफॉर द फेज स्पेस ट्रैजेक्टरी ऑफ दिस काइंड ऑफ अ स्प्रिंग मास सिस्टम मोशन शुड बी एन एलिप्स. बात खत्म. इतना सिंपल था, इसमें कुछ एडिशनल था ही नहीं. अगर हम थोड़ा सा कंपैरिजन भी करते हैं, बाय कंपैरिजन वी कैन से दैट a इज इक्वल टू 2 कैपिटल E अपॉन k रूट ओवर एंड b इज इक्वल टू 2m कैपिटल E. नाउ दिस इज ओनली द इक्वेशन ऑफ PST, राइट. डायग्राम मैंने अभी तक बनाया नहीं, तो मैं आपको डायग्राम बना के दिखा देता हूं. लेट मी शो यू बाय मेकिंग अ डायग्राम. ऑलराइट. So if I draw a diagram in, let's suppose, a graph which is kind of like 2D, okay, इस तरह से है. Alright, so this is like a 2D graph. तो यहाँ पे अगर आप देखोगे तो let's suppose the x-axis is simply representing the displacement of the spring mass mechanism or spring mass system, sorry, and the y-axis simply represents momentum or velocity. So according to this particular equation, we should get an ellipse. है ना, we should get an ellipse. तो अगर हमको ellipse मिलेगा तो ellipse will look like what? Ellipse will look something like this. Let me just draw it. Okay, draw करके मैं आपको दिखा देता हूं. Ellipse will look like this. ये होगा आपका ellipse. ठीक है? Is it clear? Visible है? थोड़ा सा मैं इसको और explain कर देता हूं. This is the phase space trajectory of a spring mass system. देखा? It was easy. It was not at all difficult. Now यहाँ पे there are of course semi major axis, semi minor axis. Semi major axis कौन सा है? Semi major axis जैसे मैंने आपको बताया, this is the semi major axis. All right, and this is the semi minor axis. All right, or rather I should say this is the major axis and the minor axis. Sorry, major and minor axis. Semi major would be the half of that. Semi major मतलब यहाँ से यहाँ तक सेमी मेजर और यहां से यहां तक सेमी माइनर. दैट मीन्स वी कैन फाइंड आउट इट्स वेरियस कोऑर्डिनेट्स. सो फॉर एग्जांपल यहां पे अगर 0 0 होगा तो व्हाट इज दिस? दिस रिप्रेजेंट्स द मैक्सिमम डिस्प्लेसमेंट along the x axis, which is x max is equal to a, which is equal to root over 2e upon k. Right, because this represents the maximum displacement. All right, and this represents the maximum momentum. Okay, जिसको मैं बोल देता हूं P max, maximum momentum, which is equal to B is equal to 2m root over E, semi minor axis. और यहां पे हम इस तरफ जाएंगे तो we will get the negative values of x and y. Now इसको मैं कोरिलेट करना चाहता हूं with the actual motion. मैं थोड़ा सा आपको और डिटेल में एक्सप्लेन कर देता हूं by correlating the whole thing with the little bit of a visual sort of a comparison with the motion. So just give me 1 second. All right, so here I have a couple of diagrams to help you understand this system a little bit better. Okay, तो आपको यहाँ पे दिख रहा है in the right hand side the spring mass system at different positions. ठीक है, तो यहाँ पे क्या है, the spring mass has been extended completely. फिर वो क्या करता है, it comes towards the equilibrium and it reaches the equilibrium which is this configuration. फिर it goes beyond the equilibrium, it gets compressed. And फिर it again expands and comes towards the equilibrium and then it again expands and goes beyond the equilibrium. ठीक है, if you can visually imagine the spring mass system motion, so you can see this sort of an oscillation that is taking place. A refers to the extreme expansion, B refers to equilibrium, C refers to the compression, D refers to the equilibrium and A refers to the again expansion. And this compression and expansion keeps on happening. Now इस चीज को थोड़ा समझने की कोशिश कीजिए, because one of the important criteria of understanding the phase space diagram is to figure out how the motion is happening. Is the motion is happening in this particular manner or is the motion happening in this particular manner? Clockwise direction में हो रहा है या anti-clockwise direction में हो रहा है? Because if you face questions on PST, तो वहाँ पे एक जो confusing area होता है, that is where should the arrows be? And to find out where the arrows should be, we should correlate the motion with the phase space trajectory values. तो यहाँ पे हम देखते हैं कि what happens at different configurations. तो सबसे पहले let's take the configuration A. What is the configuration A? The configuration A is essentially maximum displacement in the positive x-axis. ठीक है? X क्या है? X is nothing but the displacement of the spring mass system in the positive x-axis. तो मैक्सिमम डिस्प्लेसमेंट के टाइम पे क्या होता है, वेलोसिटी जीरो हो जाती है, मोमेंटम बिकम जीरो. सो एट कॉन्फिगरेशन ए वी हैव एक्स इज मैक्सिमम, राइट, बट मोमेंटम इज जीरो. तो दैट कॉरेस्पॉन्ड्स टू विच अ पोजिशन और पॉइंट, दैट कॉरेस्पॉन्ड्स टू दिस पर्टिकुलर पॉइंट. यू सी दिस, इट कॉरेस्पॉन्ड्स टू दिस पर्टिकुलर पॉइंट. पोजिशन मैक्सिमम, मोमेंटम जीरो. नाउ एज द particle comes towards the equilibrium and reaches the equilibrium, equilibrium पे क्या होता है, position becomes zero. Position means displacement, because we take the equilibrium as x का origin, so the displacement comes out to be zero. But velocity is maximum there, so therefore p becomes large, x becomes zero. But p positive होगा या negative होगा? How do we decide? Well, we decide based on the direction. If the particle is going towards the right, towards the positive x-axis, we say momentum is positive. If the particle is going towards the left, we say momentum is negative. तो यहाँ पे particle is going किधर? Towards the left, in the negative x-axis. So we say magnitude of the momentum is greatest, but the direction is in the negative x-axis, so it's negative. So then this refers to point number ये B. तो ये हो गया हमारा point number A. ये हो गया हमारा पॉइंट नंबर बी. पॉइंट नंबर बी मीन्स x इज इक्वल टू जीरो, मैग्नीट्यूड ऑफ मोमेंटम इज ग्रेटेस्ट बट डायरेक्शन इज ऑपोजिट, सो नेगेटिव, एंड बस दैट्स इट. सो देयरफॉर द डायरेक्शन ऑफ द एरो कम्स आउट टू बी लाइक दिस. सो वी आर गोइंग फ्रॉम हियर टू हियर. कैन यू सी दिस? So basically we are going in this particular direction. Now if we take this a little bit further, यहाँ से कहाँ तक जाएगा? यहाँ से it will go beyond, it will get compressed. So at this point, again position becomes maximum but in the negative x-axis and momentum becomes zero. So this becomes point number C. So this is point number C. So this is here the direction again. And then later on we have again the expansion to equilibrium. So equilibrium pe again velocity is maximum but it is directed towards the positive x-axis. So it is momentum is positive and maximum, but the displacement is zero. So this is the particular point we have. This is point number D. So this goes on and on and on like this. Okay. इस तरह से जैसे जैसे spring mass system keeps on oscillating, the phase space diagram keeps going on and on in this particular manner. So this is the phase space diagram of one given spring mass system for one given energy only. Please keep in mind that this is the spring mass system phase space diagram for one given energy. We can have multiple energies. We can have a spring mass system which is going slightly like this, you know. We can have a spring mass system that is going like this. So तब क्या होगा? Then we end up getting a family of curves. Essentially, that's it. We end up getting a family of curves. A family of curves को समझने के लिए, just let us take a look at the potential diagram. What is the potential of a spring mass system? The potential of a spring mass system is this. है ना? ये है आपका potential, this half kx square. So if we redraw this diagram, इसको दोबारा से draw कर देते हैं एक बार. So we should get a potential that looks something like this. What is the nature of the potential? If we draw the potential, then it will become clear. Just give me 1 second to draw the potential, okay? So here we have, let's suppose, okay, the potential is half kx square. So it's a bound system. So let's suppose this is x and this is v. X is equal to half kx square. Potential आपका कैसा दिखेगा? Potential आपका जाएगा इस तरीके से. So let me just make an approximate sort of a graph. ठीक है? Approximate graph बनाता हूँ. Because exact parabolo तो बनाना थोड़ा मुश्किल होगा. तो just let me make an approximate parabolic representation. So here this is the potential, है ना? अगर ये आपका potential है, वैसे दिख रहा है सेमी सर्कल, बट प्लीज़ थोड़ा पोटेंशियल ही मान के चलिए, इसको कोई दिक्कत नहीं है. जस्ट थिंक ऑफ इट एज अ पोटेंशियल. देन व्हाट अबाउट द फेज स्पेस डायग्राम फॉर डिफरेंट एनर्जीज? डिफरेंट एनर्जीज के लिए वी जस्ट गेट अ फैमिली ऑफ कर्व्स, दैट्स इट, नथिंग एल्स. ओके, सो इफ आई ड्रॉ वेरियस डायग्राम्स हियर फॉर PST, आई विल जस्ट गेट अ फैमिली ऑफ कर्व्स. सो लेट मी शो यू. तो ऑन वन हैंड let me draw 3 diagrams first and then I'll show you. So we might get this kind of a system. We might get another system that looks somewhat like this. Just 1 second. These are all ellipses with different kind of semi-major and semi-minor axis depending upon the total energy of the system. The total energy of system depends upon the amplitude, right? जितना ज़्यादा एम्पलीट्यूड होगा स्प्रिंग मास सिस्टम का, उतना ही उसका इट विल हैव ग्रेटर अमाउंट ऑफ एनर्जी. ऑल राइट, सो यू हैव अ फैमिली ऑफ एलिप्सेस हियर. वी हैव अ फैमिली ऑफ एलिप्सेस एट दिस पॉइंट. ऑल राइट, वी आर डन, वी आर ऑलमोस्ट डन. ओके, so let's make a comparison. If you look at a comparison here, this is the potential. Then let's suppose there is a particle somewhere here. Okay, there is a particle somewhere here. At this point, particle की energy, let's suppose I say is E1. So then E1 will have a trajectory in phase space in this particular manner. Okay, this is the phase space diagram for a particle having energy E1. All right, and similarly for another particle having energy, let's suppose E2. It has this phase space trajectory. What is the difference between E1 and E2? The total area, that's it. फेज स्पेस डायग्राम में सिर्फ टोटल एरिया चेंज होगा, बिकॉज द ट्रैजेक्टरी बिकम बिगर एंड बिगर एंड बिगर. इट विल एनकम्पास मोर एंड मोर एरिया, दैट्स इट, नो अदर डिफरेंस. द शेप रिमेन्स द सेम. सिर्फ सेमी मेजर एक्सिस और सेमी माइनर एक्सिस का फर्क पड़ेगा ना, बिकॉज द एनर्जी हैज चेंज्ड, है ना. यहाँ पे क्या है आपके पास? सो हियर यू हैव एनर्जी. ऑलराइट, सो द सेमी मेजर एक्सिस एंड द सेमी माइनर एक्सिस का डिफरेंस होगा. विद ग्रेटर एनर्जी दे विल ऑल्सो इंक्रीज. ऑलराइट, सो लेट मी कंप्लीट दिस. सो and then we will have here, okay, we will have here, so here the energy is, let's suppose, E3. Okay, so this will correspond to E3. So there you have it, the spring mass system, which is a very good example of a harmonic oscillator. This is the equation of PST, which gives us an idea about the the relationship between x and p in phase space, and the motion is a ellipse. Arrows are in this particular manner, and for different energies we end up getting family of ellipses. All right, आगे बढ़े. Let's move ahead to another very standard problem in classical mechanics, which is that of a simple pendulum. Simple pendulum आपको मालूम ही होगा. We have already studied simple pendulum in mechanics, we know that simple pendulum is one of those examples which inspired Galileo Galilei to, develop an insight into motion. So the second standard case is our simple pendulum example. So simple pendulum is, the motion itself is very simple. It is also similar to the spring mass system in the sense that it is also a approximation of a harmonic oscillator. मतलब simple oscillations होते हैं simple pendulum में, है ना. simple नाम में ही simple रखा हुआ है. So we get oscillations in the simple pendulum. However, उसमें थोड़े से कुछ complications हैं, मैं explain कर देता हूँ. Let me explain. So you have simple pendulum. सबसे पहले, it is not a motion that is happening in the x-axis. It is essentially a kind of rotation. ठीक है, rotation हो रहा है. The motion is restricted to the arc of a circle. Therefore, the displacement will be in terms of theta. All right. Velocity इस direction में होता है and back and forth and back and forth. Let's suppose it has a point mass m. Length of the string is L. So if we look at a simple pendulum, then what is going to be the phase space diagram as well as the equations corresponding to PST for this particular case. तो उसके लिए let us look at the energy expression. So what is the total energy of a simple pendulum? T plus V is equal to E. What is the kinetic energy? देखिए, kinetic energy होता है, यूजुअली हम बोलते हैं कि kinetic energy is equal to half m v square, है ना. But the motion here is circular. तो जब circular motion होता है, then we will have to include both the radial speeds as well as the transverse speeds. So it comes out to be how much? Half m v r square, or rather we should say r dot plus r theta dot square. ठीक है, polar coordinates है ना, we are taking polar coordinates, so we should write it in terms of polar coordinates. But because the length of the simple pendulum is a constant of motion, r dot comes out to be 0, and because the length is equal to L, so this comes out to be half m L theta dot square. However, I want to write it in terms of momentum. ठीक है, मैं momentum के terms पे लिखना चाहता हूँ. So what is the momentum of a simple pendulum? P theta क्या है? P theta comes out to be ml square omega, ml square omega or theta dot. So which means that theta dot is equal to P theta upon ml square. All right. So if I substitute this here, I will get half ml square theta dot square, but theta dot की जगह पे I write P theta upon ml square theta plus what is the potential energy? Potential is because of gravitation. So let us consider this to be the lowest point. So हम इसको V reference इसको मान लेते हैं. So अगर V reference इसको मान लेंगे तो what is this? This is nothing but L cos theta, है ना? And what is this? This is also nothing but L. So this basically comes out to be mgh. But what is h? H is equal to this height. What is this height? This height is equal to L minus L cos theta. So therefore this can be written as mgl 1 minus cos theta. ठीक है? Clear है? It is the difference between this height and this height and this height. All right. Okay. So this is simply L 1 minus cos theta. All right. Now, so this simply becomes equal to total energy E. Again, अगर हम ऐसे सिस्टम को स्टडी कर रहे हैं जहां पे एनर्जी इज अ कांस्टेंट, ओके, इफ एनर्जी इज अ कांस्टेंट, देयर इज नो डिसिपेशन, देयर इज नो ड्रैग, देयर इज नो मीडियम हियर, तो इन दैट सिचुएशन इट सिंपली रिड्यूसेस टू ml square cancel, p theta square upon 2 ml square plus mgl 1 minus cos theta is equal to total energy E. Now, the important point is that this equation itself is not going to help us figure out what is going to be the phase space trajectory because यहाँ पे cos theta का term है. And the reason is because whenever we study simple pendulum, the simple pendulum is actually not an example of a perfect harmonic oscillator. It is in fact an anharmonic oscillator. It can be approximated, however, to be a harmonic oscillator under small oscillations. तो आपने कभी नोटिस किया होगा whenever you go to college या school जहाँ पे your teacher tells you बेटा perform the experiment on simple pendulum to find out, let's suppose, the oscillation due to gravity or something like that. तो टीचर आपको बोलता है कि keep the amplitude small, बहुत ज़्यादा उसको डिस्प्लेस नहीं करना है, दूर तक नहीं लेके जाना, keep the amplitude between 5 to 10 degrees. This is because there is always this assumption that whenever we use simple pendulum to perform these kinds of oscillations, by assuming the simple pendulum to behave like a harmonic oscillator, that can only be done under the condition of small angle approximations. So therefore we are going to use small angle approximations to get an idea. Okay, and it will be interesting to see that small angle approximations में हमें क्या मिलेगा. So small angle approximations में क्या होता है, cos theta को हम reduce कर सकते हैं. Cos theta can be reduced to 1 minus theta square upon 2. So in that situation, this becomes what? P theta square upon 2 ml square plus mgl 1 minus 1 plus theta square upon 2 is equal to E. 1 and 1 gets cancelled. And what else is left? Well, this entire equation is left. P theta square upon 2 ml square plus mgl theta square upon 2 is equal to E. ठीक है. So now what do we do? Now we can sort of further simplify. E को इस तरफ लेके आते हैं. So here I'm going to say that theta square upon 2E upon mgl plus P theta square upon 2 ml square E is equal to 1. Now this is the equation of what? What is the trajectory for this particular equation if we draw a trajectory between theta and P theta? If you notice, this is similar to the earlier equation, which is the equation of an ellipse. So for a simple pendulum, under small angle approximations, we end up getting exactly the same phase space trajectory as that of a spring mass system, which is an ellipse. Why? Because a simple pendulum also behaves like a harmonic oscillator under small angle approximations. Okay, so this is the equation. This is basically the equation of an ellipse. Okay, ellipse का equation कैसा होता है? X square upon a square plus y square upon b square is equal to 1. So by comparison we can say that आपका a क्या है? What is a? A is equal to 2e upon mgl root over, and b is equal to 2ml square e. All right. So if we draw the phase space trajectory of a simple pendulum, we should get an ellipse. However, keep in mind कि हम जब ellipse की बात करते हैं, we are only finding an ellipse for the case of small angles. But what if we go beyond small angles? उसके लिए थोड़ा सा हमें qualitative discussion करना पड़ेगा. So let us do a little bit of a qualitative discussion to get an idea कि overall जो trajectory है simple pendulum का वो कैसा रहेगा. Overall trajectory. Okay, उसके लिए let me first draw a diagram. So let's suppose same ही हम करेंगे. First we will look at the potential. तो simple pendulum का जो potential energy expression है वो कैसा दिखता है? Well, if you look at the potential energy expression, it is kind of clear that the potential energy expression looks like a cos theta expression. ये दिख रहा है ना आपको? ये mgl 1 minus cos theta. ये कैसा दिखेगा? mgl को हम कांस्टेंट मान लेते हैं. 1 minus cos theta हो गया बेसिकली, है ना? So what is this? This is v theta is equal to mgl 1 minus cos theta, and this is basically theta. तो 1 minus cos theta क्या होगा? Just let me show you. So y is equal to 1 minus cos x लिख देता हूँ मैं. तो I have this math editor here. तो इससे हम प्लॉट करवाते हैं. Let's see what we get. There you have it. This is it. है ना? It's a cos theta expression. तो let us try to plot it between minus pi and pi. माइनस पाई और पाई के बीच जो है हम उसको प्लॉट करने की कोशिश करेंगे. डू यू सी दिस? बिटवीन माइनस पाई एंड पाई ये है, इस रीजन में हम प्लॉट करने की कोशिश करेंगे. सो लेट मी ड्रॉ द डायग्राम फॉर यू. सो इट गोज फ्रॉम something like this. Okay, so we are going from minus pi 0 to pi. माइनस पाई का मतलब क्या होता है? ये अगर आपका you have the simple pendulum, तो if you have the simple pendulum on a suspension point, तो अगर सिंपल पेंडुलम यहां तक पहुंच जाएगा ये 90 डिग्री हो गया, अगर कंप्लीटली वर्टिकल हो गया वहां तक चला गया वो 180 डिग्री हो गया, राइट। एंड अगर इस तरफ आ जाता है, लेट्स सपोज ये -90 डिग्री हो गया, ऑलराइट, और कंप्लीटली उधर चला जाता है तो ये -180 डिग्री हो गया। तो एक तरीके से वन कंप्लीट रोटेशन, वी आर टॉकिंग अबाउट वन कंप्लीट रोटेशन ऑफ द सिंपल पेंडुलम, ऑलराइट। सो सबसे पहले तो फॉर स्मॉल एंगल अप्रोक्सीमेशन वी एंड अप गेटिंग द इक्वेशन ऑफ एन एलिप्स। सो इसका मतलब क्या है कि फॉर स्मॉल एंगल्स, माने समवेयर बिटवीन 10 to 20 डिग्रीज और इवन लेस देन दैट एक्चुअली, in this particular region we should see ellipses as family of curves, all right. So if I draw this diagram, I should see ellipses here, okay, all right. So in this kind of a scenario I should get a couple of ellipses here. Let me first draw the diagram properly, okay. तो here we will get an ellipse. आपको याद होगा what is the direction of the ellipses? Clockwise. Last time spring mass system में जो आया था clockwise direction, यहाँ पे भी same ही रहेगा. So you'll have this kind of a clockwise direction. You'll have more ellipses, further ellipses. As long as small approximation is valid, small displacement approximation is valid, we will keep on getting something similar to ellipses. But as we go beyond small angle approximations, वहाँ पे थोड़ा सा जो है it will start deviating from ellipses. It will start deviating from ellipses. So how will it deviate from an ellipse? Well, it starts deviating from the ellipse in a very interesting manner. इसको मैं मैथमेटिकली नहीं दिखा रहा हूँ, मैं जस्ट एक विजुअली आपको बता रहा हूँ, बिकॉज मैथमेटिकली एक्चुअली ये जो इक्वेशन है विच कंटेन्स कॉस थीटा, दैट इज एक्चुअली solvable, it's not really solvable analytically, it is solvable numerically. So we can only rely on sort of numerical methods to solve that kind of an equation. So essentially what happens is that as we deviate from small angles, which means that ये जो हमारा हार्मोनिक ऑसिलेटर का अप्रोक्सीमेशन था, तो दिस इज द रीजन ऑफ द हार्मोनिक ऑसिलेटर, ठीक है, ये आपका हार्मोनिक ऑसिलेटर का अप्रोक्सीमेशन है ना यहाँ पे। तो यहाँ से जैसे जैसे हम डेविएट होते जाते हैं तो देयर इज अ टेपरिंग of the ellipse towards the sides, थोड़ा थोड़ा slight tapering आ जाता है, all right. So if I show you that there is a slight tapering that happens, all right, like the leaf of a plant or something like that, like this, okay, slight tapering that happens here, okay, something like this. As it goes even further, the tapering becomes even more intense, okay, something like this. So it is not exactly an ellipse because at large angles the potential is not exactly a harmonic oscillator, it is deviated from a harmonic oscillator, and this goes on and all till this particular point जो माइनस पाई है और जो पाई है यहाँ तक, you see this. All right, so this is the kind of a diagram, I think the best I can draw at this point, okay. The arrows will be like this, so this represents the motion. Now keep in mind that these are closed loops, because the motion is still oscillatory. मतलब अगर हमारे पास पेंडुलम है, अगर यहाँ से लेकर के पेंडुलम यहाँ तक जाता है, it is still oscillatory motion, right? But there is a possibility that we can go beyond oscillation. If I give it a large amount of energy and it has a possibility of rotating 180 degrees, so it may undergo a full rotation. If it undergoes a full rotation, then what happens is that then the phase space trajectory associated with that is actually not a closed loop, that is an open-ended curve. All right, so then we can go beyond minus pi and plus pi. Then the graph will go something like this here, okay, something like this, okay, and यहाँ पे we will see these kinds of curves, क्योंकि अगर रोटेशन होता है तो रोटेशन में कोई ऑसिलेशन नहीं होगा, तो ऑसिलेशन नहीं होगा तो it will rotate in one particular direction only. So particle which is rotating towards increasing theta will keep on going in that particular direction, and the one which is rotating towards lowering theta will keep on going in direction in this particular manner. So this is the representation of the phase space diagram of theta versus p theta for a simple pendulum, which is a combination of a few ellipses for small angles and some kind of a deformed ellipses as you go beyond small angles, and then you have these open-ended curves which correspond to complete rotation for a pendulum having energy sufficiently more so that it doesn't really oscillate but rather goes beyond it and completely keeps on circling over and over and over again. All right, so this line in the middle that you see this particular line, है ना? So this line represents the boundary between oscillations and rotations. Okay, so you have on one hand you have rotations for energies which are slightly less, and then you have for energies greater than what is required to make one complete revolution, you have rotations. So this line is known as a separatrix. Okay, separatrix. Separatrix means it separates the behavior of the PST into two distinct behaviors. So on one hand we have oscillations, and beyond the separatrix we will get pure rotations. All right, so this is the phase space diagram of a simple pendulum, and this is the phase space equation corresponding to that. आगे बढ़ते हैं. Now these were two very standard systems, spring mass system and simple pendulum standard systems, but कुछ ऐसे potentials आ जाते हैं which are a little bit more interesting and a little bit more abstract. ठीक है, one of those potentials that you might get in an examination is that of the inverted well. तो हमने यहाँ पे जो हार्मोनिक ऑसिलेटर वाला ये हमने क्या लिया था, दिस इज बेसिकली द एग्जांपल ऑफ अ हार्मोनिक ऑसिलेटर. इसको अगर हम उल्टा कर दे तो क्या होगा, व्हाट इफ वी इन्वर्ट इट, तो वी एंड अप गेटिंग एन इन्वर्टेड वेल. तो व्हाट हैपेंस इन एन इन्वर्टेड वेल, सो दैट इज गोइंग टू बी आवर थर्ड एग्जांपल, थर्ड केस स्टडी. ठीक है, तीसरा जो केस स्टडी है दैट इज एन इन्वर्टेड वेल या फिर इन्वर्टेड हार्मोनिक ऑसिलेटर. हार्मोनिक ऑसिलेटर. सो हार्मोनिक ऑसिलेटर का जो पोटेंशियल होता है, व्हाट इज द पोटेंशियल ऑफ हार्मोनिक ऑसिलेटर, इट इज Vx इज इक्वल टू हाफ के एक्स स्क्वायर. तो इन्वर्टेड जो वेल है उसका माइनस आ जाएगा यहाँ पे, दैट्स इट, एक माइनस लग जाएगा. ठीक है, सो डायग्रामेटिकली स्पीकिंग द इन्वर्टेड वेल लुक समथिंग लाइक दिस. जस्ट गिव मी अ सेकेंड. The diagram of an inverted well looks something like this. So if I draw the diagram here, it will look something like this. All right, so here you have x, here you have Vx, and the shape is essentially like this. Shape is essentially in this particular manner. तो इसको अगर हम थोड़ा सा सही तरीके से प्लेस कर देते हैं, let me put it like this, थोड़ा सा इसको एस्थेटिक बनाने की कोशिश करते हैं. ओके, हाँ, now it looks nice. Okay, all right, so now what is the phase space trajectory for this? तो phase space trajectory को हम तो वैसे डायग्रामेटिकली भी मैं इसको एक्सप्लेन कर सकता हूँ, बट सबसे पहले लेट मी डू इट बाय लुकिंग एट द मैथमेटिकल इक्वेशंस. दैट्स द सेफेस्ट वे, है ना. सेफेस्ट तरीका है कि मैथमेटिकल इक्वेशंस को हम देख के लेट अस मेक अ कंक्लूजन अबाउट द नेचर ऑफ द फेज स्पेस ट्रैजेक्टरी. अदरवाइज वी माइट गेट इनटू ट्रबल. सो दिस इज x एंड दिस इज px. तो मैथमेटिकल इक्वेशन को अगर हम देखेंगे, px की जगह p लिख दिया सिर्फ. ठीक है, तो सबसे पहले तो यहाँ पे ये है, हाउ इज दिस डिफरेंट फ्रॉम द अर्लियर एग्जाम्पल्स. इज डिफरेंट फ्रॉम द अर्लियर एग्जाम्पल्स in the sense that the motion is not going to be bounded. पहले के जो examples थे in the simple pendulum, the particle was stuck here, right? I mean, the system was stuck here. I should not say particle because simple pendulum is oscillating like this, but the system is stuck in terms of its energy. here. Beyond it, of course, the system is not stuck, but यहाँ पे it is stuck here. So the simple pendulum is a good example of both bounded and unbounded motion. So यहाँ पे in this region, the particle is stuck. Beyond it, it is not stuck. Harmonic oscillator में it is always stuck. You know, in this example, inverted well में it is never stuck. It is always unbounded motion. So motion is not bounded here. Motion is unbounded, and this is an important point. Motion is unbounded. मतलब जो भी particle होगा, जो भी system होगा, it will interact with the potential, but it will come from infinity and go back to infinity. It will never be restricted to one given region. So particle will come from plus minus infinity, interact with the potential, and go back to plus minus infinity. It is not bound to any kind of a region. अगर हम let's suppose इसकी Hamiltonian को check करते हैं, let's suppose we look at the Hamiltonian. So T plus V is equal to the total energy. What is T? T is equal to P square upon 2m. V is minus half kx square is equal to E. Now tell me something. Okay, now if I simplify this equation, it becomes P square upon 2me minus x square upon 2e upon k is equal to 1. Now tell me, this is an equation corresponding to what? थोड़ी देर पहले हमें जो equations मिला था, p square plus x square is equal to 1 वाले जो equations थे, they were ellipses, and p square plus theta square plus is equal to 1 वाले भी ellipses थे. ये किस तरह का equation है? You know, this is very interesting. If I say y is equal to x plus c, what is this? This is a straight line. If I say y is equal to x square, what is this? This is a parabola. If I say x square plus y square is equal to 1, what is this? This is an ellipse. But if I say x square minus y square is equal to 1, this is what? This is a hyperbola. Okay, this is the equation of a hyperbola. तो कुछ चीज़ों को आपको याद रखना पड़ेगा. By the way, मैंने थोड़ा सा एक गलती कर दी यहाँ पे, है ना? I should have kept it as x square minus px square, but it doesn't really matter. It doesn't really matter. No, it's fine, perfectly fine. It doesn't really matter because यही आएगा p square minus x square के terms में आएगा. So this is the equation of hyperbola. ठीक है? Hyperbolas are open-ended curves. Open-ended curves, and they will correspond to the motion of the particle as the particle approaches this kind of a potential. Now इस चीज को समझने के लिए ना हमें कुछ case studies करने पड़ेंगे in terms of particles that approach this system. ठीक है, कुछ particles को हम लेते हैं which is approaching, और आप इस चीज को थोड़ा ध्यान से समझने की कोशिश कीजिए, because if you understand it, only then you will completely understand. If you understand the motion of the particle, only then you will completely understand the phase space trajectory. ठीक है, इस चीज को हाईलाइट करने के लिए लेट मी फर्स्ट ड्रॉ 2 लाइंस हियर. अब मैं इन लाइंस का इंपॉर्टेंस थोड़ी देर बाद में बताऊंगा आपको. थोड़ी देर बाद में आई विल एक्सप्लेन द इंपॉर्टेंस ऑफ दीज लाइंस. अभी मैं जस्ट इसको रेफरेंस के लिए ड्रॉ कर रहा हूँ. आई एम जस्ट ड्रॉइंग इट एज अ रेफरेंस हियर. ओके, टू कीप इट एज अ रेफरेंस हियर. ओके, ऑलराइट. नाउ लेट अस think of it in this particular manner. If there is a particle which is approaching this system from infinity. So for example, let me take a particle that is approaching from the right. Okay, I call this as particle 1. Let's suppose the particle has energy E1. Okay, negative energy hai, some random negative energy. It is approaching from the left. So if it is approaching from the left, so it has x variable is, sorry, my mistake, it is not approaching from the left, it is coming from the right and towards the left. Particle is coming from the right but towards the left. So x is initially positive and momentum is initially negative because it is directed towards the negative x-axis. Fine. Then what happens? It interacts with the potential and it gets reflected backwards. It doesn't have enough energy to penetrate through because we are in classical mechanics. This is not quantum mechanics. In quantum mechanics we have tunneling, but here in classical mechanics there is no such thing as tunneling. Okay, So it interacts with the potential, gets reflected and go backwards. So initially what happens is x is, positive. So x is somewhere here, x is positive, momentum is negative, momentum is somewhere here, and then after reflection it again goes back to positive infinity. So x is again positive and momentum is also positive. So some kind of a motion happens like this. So you'll get some kind of a graph, a hyperbola that looks something like this. So this is point number 1. This is the arrow. Okay, this is the hyperbola. You can have other particles also. For example, you can have a particle that is having a little bit slightly greater energy. Particle number 2 again gets reflected backwards and goes back, something like this, or maybe a little bit lesser energy. Let me take a lesser energy, it will be easy to draw the diagram. Another particle comes and interacts and goes back. Point number 2, it will have a hyperbola similar to particle number 1, like this. So point number 2. Okay, can you understand it? Okay, perfectly fine. Now let's look at the other direction. What if we have another particle, particle number 3, having energy E3 that approaches from the left? It gets reflected and goes back again. It has energy E3. All right. So initially what happens? The particle is at negative x-axis. Because it is directed towards the right, it has positive momentum. So it should start somewhere here. But after it gets reflected, it goes again to negative infinity. But momentum now also becomes negative. So it goes somewhere here. So you will have something like this. So you should get a graph that looks something like this. Okay, so let's suppose this is point number 3. So this is the curve for particle number 3. If we have another particle, let's suppose a particle number 4 with a little bit even lower energy, it also comes, strikes the wall, gets reflected back. So we will have another hyperbola in this particular direction. This is particle number 4. What about if a particle has energy which is positive? Okay, if a particle has energy which is positive, then what happens? So let's suppose there's a particle which is coming from the left, particle number 5 going towards the right. Now this particle has energy greater than Vmax. Okay, what is Vmax? This is Vmax. This is the maximum potential energy. So it means the particle will not be reflected back, it will keep going forward. So that means its momentum is always going to be positive. However, there is going to be a change in the momentum. So the graph corresponding to this particle is, it approaches from negative x-axis, goes towards the positive x-axis, momentum always remains positive. However, the magnitude of momentum changes. Why? As the particle approaches the potential maxima, its kinetic energy slowly decreases. If kinetic energy slowly decreases, momentum is also going to slowly decrease in magnitude, which is what's happening. And then as it goes beyond this maxima to the other side, its kinetic energy will slowly increase, and because kinetic energy slowly increases, its momentum is also going to slowly increase. That is what's happening. Alright, what is kinetic energy? Kinetic energy is difference between total energy and the potential energy, therefore is related to the momentum, right? The relationship between momentum and potential energy is given by 2m E minus Vx, right? From the usual sort of a E is equal to P square by 2m plus V formula, right? So this is the hyperbola for this particular graph. We can have other hyperbolas here for other particles, similar particles having similar energy. If I take another particle, let's suppose particle number 6 coming from the right, going towards the left. So it is going to going from positive infinity to negative infinity, but momentum is always negative, keep in mind, because it is always directed in the negative x-axis. So for that, here we will have a hyperbola here. This is the hyperbola corresponding to that. Okay, so this is point number 6. So as the particle approaches, its magnitude in kinetic energy decreases, therefore magnitude in momentum decreases, and as it goes past Vmax, its magnitude increases, but it always remains negative because it is directed towards a negative x-axis. And similarly, you can have other graphs. Alright, so now I think you have a much better, clearer idea of how to draw phase space diagrams. Now, you remember these two lines that I made in the center, these straight lines? What are these lines? You know, these are very interesting lines because they correspond to the scenario where the particle's energy is equal to Vmax. Okay, so they correspond to a special case scenario here. Special case. What is a special case? Special case is that E is equal to 0. Okay, or E is equal to Vmax because Vmax is 0. Now, what happens if E is equal to 0? Then we can take a look at the equation. Let's take a look at the equation. Okay, let's take a look at the equation if E is equal to 0. So, if E is equal to 0, then we have P square upon 2m minus half kx square is equal to 0, which means that we have P square minus kmx square is equal to 0, which means that we have P square is equal to kmx square, or we have P is equal to plus minus root over kmx. Now, however, the equation of the phase space diagram for E is equal to 0 is slightly different. P is equal to plus minus root over kmx. This is not the equation of a hyperbola. This is the equation of a straight line. Okay, this is the equation of a straight line. So, these two lines, they are basically the phase space diagrams for those particles which have energy E is equal to 0. That's it. Okay, so let's suppose there is a particle, point number 7, which is approaching from the left. Let's suppose point number 7, which is approaching from the left. So, then it is starting from negative infinity, fine, but its momentum is positive. So, therefore, this is that particle. It comes towards the barrier. Now, once it reaches the barrier, it might get reflected back because its energy is exactly equal to Vmax. So, therefore, it might get reflected back also, it might get transmitted through also because the total energy is exactly equal. So, it might go forward in this particular direction or backward in this particular direction. Similarly, if we talk about another particle, particle number 8 coming from the right, this is the particle 8 coming from positive infinity, goes here, and it might get reflected back or it might go forward. So, this is the phase space diagram for an inverted well. Alright. Only by comparing the motion of individual particles having different energies and how they interact with the system, how their momentum changes as they get reflected backwards, by doing that analysis, we can actually draw the proper diagram with proper arrows. बहुत बार क्या होता है कि आप एग्जाम में इस तरह का कोई क्वेश्चन आ जाता है जहां पे आपको सिमिलर डायग्राम्स दिया जाता है बट एरोज आर गोइंग टू बी डिफरेंट. देयर यू माइट गेट कंफ्यूज्ड, यू नो, कि एरोज का क्या चक्कर है, which is the correct diagram. Well, for that you have to make a comparison with individual cases. पार्टिकल अगर राइट से आ रहा है, रिफ्लेक्ट बैक हो रहा है, तो मैग्नीट्यूड के मोमेंटम में क्या चेंज है? पहले नेगेटिव था, फिर पॉजिटिव हो गया. पार्टिकल लेफ्ट से आ रहा है, तो मैग्नीट्यूड ऑफ मोमेंटम, मोमेंटम के उस वैल्यू में क्या चेंज है? तो इफ यू हैव अ लिटिल बिट ऑफ एन अंडरस्टैंडिंग ऑफ दैट, then you can find out which the right diagram is. Now, let us move forward to the next case study, which is the fourth case study that we have, which is that of a double well potential. Double well का मतलब क्या है? It looks like a W. It looks like a W. Okay. W कैसा दिखता है? W ऐसा दिखता है. यही आपका डबल वेल. यूजुअली हम जब वेल बोलते हैं, हार्मोनिक ऑसिलेटर इज वन एग्जांपल ऑफ अ वेल, है ना? इट्स अ वेल. इनफाइनाइट स्क्वायर वेल में क्वांटम मैकेनिक्स में हम ये पढ़ते हैं रेक्टेंगुलर पोटेंशियल वेल. हार्मोनिक ऑसिलेटर इज अनदर वेल. बट अगर मैं इसको थोड़ा सा ये शेप दे दूं तो ये हो गया आपका डबल वेल, विच इज ऑल्सो एन इंटरेस्टिंग प्रॉब्लम. स्टैंडर्ड का केस ही आप मान सकते हो. ठीक है, तो डबल वेल पोटेंशियल के लिए मैं आपको एक पोटेंशियल का एग्जाम्पल दे देता हूं. सो फॉर एग्जाम्पल, यू हैव वी एक्स इज इक्वल टू माइनस एक्स टू द पावर 4 माइनस एक्स स्क्वायर. दिस इज एन एग्जाम्पल ऑफ अ डबल वेल पोटेंशियल. आपको कैसे मालूम? वेल, वी कैन डू एन एनालिसिस इफ यू आर इंटरेस्टेड. करें एक छोटा सा क्विक एनालिसिस कर देते हैं. एक छोटा सा एनालिसिस कर देते हैं कि हम कैसे एनालाइज कर सकते हैं कि किसी भी पोटेंशियल को हम डायग्रामेटिकली कैसे एनालाइज कर सकते हैं। देखिए, मेनी टाइम्स व्हाट हैपेंस इज दैट इफ यू गो इनटू एन एग्जामिनेशन you might not be given a diagrammatic representation of the potential. No, you might be given a mathematical function of the potential. फिर आप क्या करोगे? Well, then what you do is, the first thing that you do is you try to look at the extremum points. Find out extremum points. ठीक है? Extremum points में क्या हो सकते हैं? आपको मिनिमा मिल सकता है या फिर मैक्सिमा मिल सकता है, या फिर यू कैन हैव अ कॉम्बिनेशन ऑफ लोकल मिनिमास एंड लोकल मैक्सिमास. दीज आर टू पॉसिबिलिटीज. नाउ वंस यू गेट एन आइडिया अबाउट लोकल मिनिमास एंड लोकल मैक्सिमास, देन यू कैन हैव एन आइडिया अबाउट द फेज स्पेस ट्रैजेक्टरी. व्हाई? टू अंडरस्टैंड. लेट्स गो बैक. ठीक है, अभी हमने इतने सारे केस स्टडीज करे हैं, so now we can generalize certain things. तो यहां पे क्या है हमारे पास? When we looked at the harmonic oscillator, what was this? This was a minima. Okay, and if we have a perfect harmonic oscillator, we will have a family of ellipses. But let's suppose we don't have a perfect harmonic oscillator. Even then, for small displacements, we can always approximate the minima as a harmonic oscillator. So in that case, we'll still get ellipses near the minima. समझ में आ रहा है? Which is this example perfectly. We get ellipses near the minima, right? So whenever you have a system in which, if you do a potential energy analysis, you find a minima in the potential energy diagram, you can be rest assured that in the phase space diagram you will get these closed loops resembling ellipses. Now, what if you get maxima? Maxima के लिए मैंने आपको ये example दे दिया. What is this? This looks like a maxima, right? It looks like a hill. So when you get a hill, what do you get? You get these kind of open-ended curves, which are essentially hyperbolas or resembling hyperbolas. So what we can conclude is, if you get local minimas, you will get ellipses or something resembling ellipses there, or something resembling ellipses in that particular vicinity. And if you have local maximas, you will get something resembling local hyperbolas. Okay, local hyperbolas बहुत ही important है. What are ellipses? Ellipses are closed loops. What are local hyperbolas or hyperbolas? These are open-ended curves. Open-ended curves. ठीक है, it comes from minus infinity, goes to plus minus infinity, कोई अंत नहीं है. So this is one way of analyzing different kinds of potentials, that if you are given a mathematical function, find out the extremum points. If you find minimas and maximas, then rest assured that near the minima in the phase space diagram, you will get closed loops resembling ellipses, and near the maxima, you will get local hyperbolas or open-ended curves. All right. So इस potential को एक बार मैं दिखाता हूँ. How can we do that analysis here? So to do that analysis here, I want to find out the extremum points. तो इसके लिए क्या करेंगे? We will do a derivative. dv upon dx is equal to 0. So d by dx of x to the power 4 minus you have x square is equal to 0. So this becomes 4x cube minus 2x is equal to 0. So this becomes, एक तो आंसर इसमें आएगा x is equal to 0 और दूसरा आंसर इसमें आएगा 4 एंड दूसरा आएगा आपका 4x square is equal to 2, right? So this comes out to be x square is equal to half or x is equal to plus minus 1 upon root 2. Fine. So we essentially have 3 points. We have 3 points. Now we just need to be sure whether they are minimas or maximas. तो देखते हैं. तो फॉर एग्जाम्पल यू हैव x इज इक्वल टू 0 पे क्या होगा, और यहां पे हम देखते हैं x इज इक्वल टू प्लस माइनस 1 अपॉन रूट 2 पे क्या होगा. ओके, सो फॉर दैट वी नीड टू डू अ सेकेंड ऑर्डर डेरिवेटिव d2v अपॉन dx2 एट x इज इक्वल टू 0 अगर हम करेंगे. सो दिस विल बी d अपॉन dx ऑफ 4x क्यूब माइनस 2x. दिस इज इक्वल टू 4 into 12x minus 2. So at x is equal to 0, this becomes minus 2. So this is less than 0. इसका मतलब x is equal to 0 is a what? It is a minima. All right. If the second order derivative, no, it's a maxima, sorry. It's a maxima. So if the second order derivative is less than 0, it's negative. That means x is equal to 0 is a maxima, or at least a local maxima. Fine. Now, next case scenario. Here, you have d2 v upon dx2 at x is equal to plus minus 1 upon root 2. What is this? This is equal to d by dx of, again, 4x cube minus 2x, and then we have this is equal to 12x minus 2, but at x is equal to plus minus 1 upon root 2. This is going to give me, oh no, I should get square here, okay, 12, 4 into 12 x square. So this is 12 into 1 upon 2 minus 2 is equal to 6 minus 2 is equal to 4, which is greater than 0. If we have greater than 0, then we have a minima. So that means we have two minimas here. X is equal to plus minus 1 by root 2 are minimas. Okay, so as I said, in examination you can be given a potential function but not a diagrammatic representation. Then what you have to do is, based on your estimates, you have to figure out the sketch of the potential. So agar I am saying that this is the x-axis and this is the v-axis, and x is equal to 0 corresponds to a maxima. So there is a maxima somewhere here. And there are 2 points, plus minus, let's suppose plus minus 1 by root 2, there are 2 minimas here. So how can you make sense of this? There is some kind of a maxima here. There is some kind of a minima here. Okay, this looks something like a W. Now this makes sense. Right? Now this makes perfect sense. Do you see that? There is a maxima at x is equal to 0 and 2 minimas at plus minus 1 by root 2. Okay, I can show you using my math editor. So if I say this y is equal to x to the power 4 minus x square, y is equal to x to the power 4 minus x square. If I plot this, what should I get? Let us check. All right, here you see this. You see the W. This is a double well potential. This is a double well potential. Let us insert this here. Okay, let me use this only to draw the diagram. All right. Now, how can we draw the diagram here? To draw the diagram, what we are going to do is, we are going to do a little bit of a approximation. What did I say? I said that you can make a comparison by looking at local maximas and local minimas. Okay. This is the crux of the matter. This is the basic crux, that if you get minimas, okay, if you get minimas, you have to be sure that they are going to be closed loops looking like ellipses in that region. And if you get maximas, they are going to be open-ended curves looking like, local hyperbolas. So based on this analysis, we can sort of get an idea ki what sort of a diagram we can get. So what we get is something like this. We'll get something interesting. Let me show you. काफी इंटरेस्टिंग सा एक डायग्राम बन जाता है. So what we will get is, these are the local minimas, right? So these are the local minimas here. So let me draw a diagram. So this is the local minima. This is the local minima. So what I'm going to do is, I'm going to draw ellipses here. Of course, you won't have complete ellipses. After some time, as you deviate from the minima more and more, these ellipses are going to also get deformed in its shape and get tapered, slightly tapered here and there. But at the center, you will have these closed approximate ellipses, ellipse looking objects. So this is an ellipse. And you have another ellipse here, and you have another ellipse here. Okay, so these are all closed loops, because whichever particle is having energy and is stuck in that local minima is kind of stuck in a region. Therefore, these are closed loops. Okay, these are closed loops. Another closed loop here. All right. Now these are closed, very interesting looking loops. Now, As we go further and further away, these local ellipses start getting deviating, deformed in its shape, okay, slightly deformed in its shape, because it's difficult to predict. So I'll give you a qualitative sort of an interpretation. Slightly difficult to predict mathematically, but it might look something like this. Just give me 1 second. Let me draw another ellipse. It might look something like this. Okay, so here slight tapering of the ellipses. Here all right, beautiful. Okay, you see this is also closed loop, but it's not exactly an ellipse. It got slightly tapered to this side. Okay, another. All right, beautiful. So these are the closed loops for objects which are stuck in this region. Okay, so for the particles which are stuck here, these are the closed loops you will have, because closed loops in phase space diagram correspond to particles which are stuck in a region and somehow are experiencing some kind of a circular oscillatory motion. Now, what about particles beyond this? Okay, now beyond this, these particles are also stuck, but not in the small minima, but in the overall potential. But as a particle is going from, let's suppose, here to here, what is going to happen? Because of the differences in the potential energy, the kinetic energy is going to slowly increase and then decrease and then increase and then decrease. So therefore, the momentum is also going to slowly increase and decrease and increase and decrease. Okay, let me draw the diagrams. You are supposed to get hyperbolas near the maximum, remember? So these are not exactly hyperbolas, these are like local hyperbolas. Okay, so you will have something like local hyperbolas that look like this. Okay, local hyperbolas that look like this near the maxima. You see this? Near the maxima, you get these local hyperbolas. However, as you go away from the maxima, the particle is not really in a completely unbounded situation. It is bounded. Therefore, it is going to sort of come back. So therefore, you end up getting these situations. So if I continue this curve, there you have it. This is the phase space diagram of a double well potential, guys. Okay, double well potential. All right, that is all. हमने आज spring mass system को देखा. All right, for oscillatory motion we get ellipses as phase space diagrams. We saw simple pendulum. We got for small angle oscillations we get ellipses, but for beyond it we get certain deviations. We saw an inverted potential where we got hyperbolas, and then here we have the double well potential. So I hope you have understood that these standard cases, standard problems, and their corresponding phase space diagrams, and based on my suggestion of this particular analysis, if you get any kind of a potential in an examination, all you have to do is just try to figure out the nature of the potential in a diagrammatic manner. Try to figure out the position of the minimas and the maximas by finding out the extremum points. And then near the minimas, try to fit into ellipses and closed loops. And near the maximas, you have some kind of a local hyperbolas. And whatever option best approximates that will be the correct answer. So that is all for today. I am Divya Jyotidas. Thank you so much, guys. I hope you learned something from today's lecture. I will see you in the next video. Take care. Bye-bye.